Hello everyone, this is Mr. Jackson. We're going to be picking up with part 2 of our Module 2 lecture presentation on the blood. And we're going to be starting this part by looking at the process of blood cell formation. It applies to all of the different formed elements. We have a official term for this process that we call hematopoiesis. This is referring to blood cell formation. It's important to keep in mind, most blood cells do not divide. So stem cells that exist in our red bone marrow, like you can see here, ultimately are going to be responsible for helping to make replacement cells. So a lot of these cells do not divide. For example, our red blood cells, and red blood cells might have, a normal lifespan of about 100 to 120 days. And so it's important that we constantly have this ongoing process of hematopoiesis to replenish those number of red blood cells, as we can expect to lose them again every 100 days or so. We have a key player here, a hormone that actually helps regulate this process. It's called erythropoietin. This is the hormone that basically will regulate the formation and destruction of red blood cells. This hormone's primarily made in the kidneys, also to a lesser extent in the liver, but primarily the kidneys. And it tends to be triggered by a drop in your normal blood oxygen levels. A drop in those blood oxygen levels is going to indicate that, hey, I need to stimulate some increased red blood cell production so that I can help circulate more oxygen and get this content up. And so typically that's going to be the stimulus that triggers the kidneys to create or release more of this erythropoietin. And that erythropoietin is going to be going to stimulate in the red bone marrow the process of hematopoiesis. And before moving forward, I do want to make sure that we address how all of these different types of blood cells come into existence. It's always going to start with what's called a hemocytoblast stem cell. These are going to be the stem cells that can ultimately further differentiate into any type of blood cell. The secondary stem cells will either become lymphoid or myeloid. If they become lymphoid stem cells, those can only further differentiate to form the lymphocytes. These are going to be the white blood cells we can expect to find in the lymphatic system. But if they differentiate into myeloid stem cells, these can become every other type of formed element in the blood. These can become our red blood cells, our platelets, and every other kind of white blood cell that is not a lymphocyte. So I want to break down some key facts here whenever it comes to red blood cell formation. Now, remember, these are anucleate. They don't divide, they don't grow, they don't synthesize their own proteins, and they tend to wear out after about 100 to 120 days. Now, when these red blood cells are worn out, they are going to be eliminated by some phagocytes circulating in the blood. And these are specifically going to break these red blood cells down in the spleen or the liver. Lost cells are going to be replaced by the ongoing division of these hemocytoblasts that we just covered in the previous slide. You can find those in the red bone marrow. And then the rate of red blood cell production is again controlled by that hormone, erythropoietin. The kidneys are what produce that erythropoietin in response to reduced oxygen levels. And ultimately, this means that our homeostasis in this system is going to be maintained by a negative feedback loop, ultimately controlled by our blood oxygen levels. So if we have that squared away, we're pretty good on red blood cell formation. And I also wanted to provide a really useful image, an illustration of this point, where it kind of gives you a step-by-step process for how our red blood cell production is regulated. So it's always going to start with a stimulus. This happens to be low oxygen content in the blood, or more specifically, low oxygen carrying ability. And this can be due to a few things. It can be lower red blood cell count. It can be a decreased amount of hemoglobin, which can actually bind to the oxygen. It could be a decreased availability of oxygen, like if I'm holding my breath. And that's ultimately going to trigger the kidneys to release erythropoietin. This erythropoietin goes to stimulate red bone marrow, and then that red bone marrow is going to basically experience some enhanced erythropoiesis, some red blood cell formation, which is going to increase our red blood cell count. And that ultimately, by increasing the red blood cell count, we hope will lead to increased oxygen carrying ability of the blood overall. Okay, so we covered how new blood cells come into existence. The next thing that we want to make sure that we cover as a part of this conversation, as part of this module, is the process of blood clotting. Very, very important process when it comes to the blood. So we want to make sure that we understand, at least generally, how this works. So the official name for the process of blood clotting is hemostasis. This is referring to the fast and localized process that the body uses to stop bleeding when a blood vessel becomes damaged. This happens in 3 distinct phases. It's going to start with what we call vascular spasm. This is where your smooth muscles in that damaged blood vessel will ultimately contract, and then you'll experience what we call vasoconstriction. This is a narrowing of the blood vessel, and this will ultimately go to slow down blood flow so that we don't experience increased loss of blood. So we're going to vasoconstrict, contract those smooth muscles in order to further restrict blood flow. We don't want more or normal blood flow happening in this area. The second phase is our platelet plug formation. This is where our platelets, again, those key players in creating blood clots, they're going to gather and they're going to adhere to the site of damage. Where we have that damage, what we're going to see is we actually have now exposed some inner collagen fibers. The platelets can grab onto that, and they can also grab onto each other. They're very sticky that way. And by grabbing on to that site, they're able to basically create what we call a platelet plug. So we're going to plug that hole where the damage is so that we don't continue to lose, a lot of blood from that vessel. And then the third phase is coagulation. This is where you have a whole lot of various clotting factors creating what we ultimately would call a clotting cascade. There is a whole lot going on here, a whole lot of clotting factors with specific names, calling other clotting factors to the site. But a key player in this process is fibrin. And fibrin proteins are what are actually going to help form this sort of meshy clot that will ultimately finish closing the gap and begin the healing process of that damaged blood vessel. And so I wanted to further break down, this is a very useful image where it basically breaks down each of these 3 phases. You can feel free. I'm not going to just, read each and every one of these off to you because we've already gone through a general description of what these mean. But if you'd like to, go ahead and pause the video. Importantly, you have this fibrin mesh. This is actually what this looks like under a scope. And then some important things to know. Blood will usually clot within about 3 to 6 minutes. The clot remains as endothelium is regenerated, and ultimately that clot is going to be broken down after the tissue is repaired. Another important thing to know is that if you experience some sort of an injury and you are losing blood, this first step right here for vascular spasm, this is actually why it's effective to apply pressure to that point of injury, because we will actually increase the amount of smooth muscle contraction, further vasoconstricting in that area. So we actually decrease more the amount of blood that's coming to that area. So if you have an emergency or any type of injury, you can apply pressure to an area where we're losing blood. That will help phase 1. And then especially useful is we don't just want to use our hands, but if you have some sort of sterile gauze, that is also extremely, extremely effective, because the platelets that are coming in and sticking to the collagen fibers, or they're sticking to each other, the sterile gauze will actually give those platelets something else to stick to. So it can be extra helpful in that regard as well. Really quick, some homeostatic imbalances that we might see whenever it comes to blood clotting. Two major categories. We have it where we would have undesirable clotting. This is basically where we don't really have damage to the blood vessels, but we're clotting anyway. Okay, so whenever we have a clot developing and persisting, and it's not because of a damaged blood vessel, we call that clot a thrombus. Okay, so a thrombus is just a fancy word for a blood clot. But these can be deadly in areas like the lungs if those blood clots cut off blood supply and oxygen content and nutrients, leading to cell and tissue death, right? So it's a very serious situations where the bigger the clot, the worse the potential for blocking entire blood vessels. And if we cut off supply to certain areas, tissue death is likely to result. Now, if a thrombus, a blood clot, breaks away from its original site and is just kind of free floating in the bloodstream, then we would call it an embolus. And an embolus is also, again, it can become severe because basically it's just floating around, and it can later clog vessels in other critical areas where we didn't initially have that thrombus develop. So if an embolus, by example, were to travel to, blood vessels that supplied the brain tissue and were to occlude an entire blood vessel, we might experience something like a stroke. And then you have bleeding disorders where we can't clot as much as we need to. So you have two that we're going to look into. First one is thrombocytopenia. Thrombocytopenia is just basically where you have an insufficient number of circulating platelets. This is arising from a condition that basically suppresses your bone marrow. So this can basically, even normal movements, cause bleeding from small blood vessels that require platelets for clotting. And this is typically evidenced by something called petechia, and this is referring to small purple blotches on your skin. And then the more common one, probably the one that you've heard of before, is hemophilia. This is a hereditary blood disorder. Normal clotting factors are typically missing, and minor tissue damage can ultimately result in life-threatening, prolonged bleeding. Okay, so it's a very serious situation. These disorders, again, two categories: where we overclot and where we don't clot like we should. And I want to finish our conversation, our second part of this lecture, by going a little bit more into blood types and blood transfusions. Can't go through a conversation about the blood without covering these two main things. So, blood transfusions, the need for them. Large losses of blood can have serious consequences. If we lose anywhere from 15 to 30%, it would cause pale skin and body weakness. But if we lose over 30%, this is going to probably throw your body into a state of shock, and this can also be fatal. So in those instances where we are losing substantial amounts of blood, in those more severe or emergent circumstances, blood transfusions can be that saving action that we can take. And so it's important to understand that whenever we receive blood transfusions, so, maybe from like a blood donor, right? So whenever we're receiving transfusions, it's really, really important for us to receive transfusions that are of the same blood type, or of a certain blood type that our bodies can allow. Reason being, because if our red blood cells happen to break down, term called lysed, if we happen to break down or attack these transfused blood cells, this will release the hemoglobin within them into the bloodstream, and all that free hemoglobin can further block kidney tubules, and that can cause kidney failure, which could also result in death. Less severely, it can cause fever, chills, nausea, vomiting. A lot of bad things can happen if we receive transfusions with incompatible blood types. And so we want to understand what those blood types are and what they mean. So a really basic overview: all cells have a glycoprotein or glycolipid marker or tag, and we call these tags antigens. Now, if your body recognizes cells that have different antigens from it, they're going to perceive that as foreign, right? So, and if we receive any sort of word that these antigens are foreign, we are going to initiate an immune response, or an attack response is going to be activated, right? We're going to get rid of that because we recognize that it doesn't belong. Now, these recognizers, these ones that actually do, the analysis here, are referred to as antibodies. And these respond to antigens by binding to them and then clumping, or a term that we're going to use, agglutinizing or agglutinating cells together for their destruction. So it causes clumping of these cells for destruction. And red blood cell antigens, we specifically call those agglutinogens. And blood type, your blood type, is ultimately going to be determined based on the presence or absence of what we would call A and B agglutinogens or antigens. And so we want to break this down. So this is a really, really useful table that gives you a full breakdown of the various blood types and what they mean and how they act. So we have blood type AB. What this means is that on the surface of your red blood cells, you have these markers, these antigens that are for both A in yellow and B. They're like little identifiers that say that, hey, these are familiar, not foreign. And so basically, because you have both A and B antigens on that surface, you're not going to create any antibodies to assess anything that's other. You have the two that you need. So if you have type A blood, this is going to mean that you only have those A antigens. And so basically what that's going to mean is, because you only recognize the A antigens, you are going to create anti-B antibodies, right? These are going to be antibodies that specifically seek out and attack B antigens because they're not familiar, they're foreign. If you have type B blood, it's just the opposite, right? At this point, B antigens are on the surface of your red blood cells. That is what's recognized as familiar. And then we're going to create anti-A antibodies, which would then attack any A antigens that are going to be in the blood. They recognize them as foreign. And then finally, the last blood type is going to be type O. This is where you don't actually have A or B antigens on the surface of your red blood cell. And so you're going to end up creating anti-A and anti-B antibodies. If you see A antibodies, A antigens or B antigens in your bloodstream, either of those, both of them, are going to be recognized as foreign, and they will initiate an immune response and be attacked. So the way to think about this, the reason why this matters, especially having already addressed transfusions, is because this will ultimately affect what blood types you can receive from donors, and what blood you would donate and who could receive that. So if you're blood type AB and you have both of those antigens and you don't create any antibodies, that means that you're able to accept A because you recognize it, B because you recognize it, AB because you recognize both, and O because O wouldn't pose any threat. It doesn't have anything that would be considered foreign. If you have type A blood, the only two that you're able to receive are the ones that are familiar, which is other A's, or O blood, because again, they don't have any antigens that would be recognized as foreign. For B type blood, you'd have B antigens. You can receive other B antigens, or again, type O. And if you're O type blood, the only thing that you're not going to recognize as foreign is other O type blood. And so there are two distinct terms that we often assign to two of these blood types. If you are blood type AB, and you can receive literally any other type of blood, we call people with type AB blood universal receivers, because they can accept everything. And then for people with type O blood, being that they can only accept O, but they can donate O to literally any other blood type, we call people with O-type blood universal donors because they can donate to anybody. And so if you happen to have O-type blood, it is especially useful for you to consider donating your blood regularly. And finally, we are going to finish up our conversation today by going a little bit further into blood types because we also have these factors that are referred to as rhesus or Rh factors. They're called that because initially one of the 8 types of these rhesus antigens were observed in rhesus monkeys. And obviously we've since recognized these in humans, but that was where that name came from. So these Rh factors can be either positive or negative. Think of these as additional antigens that could be on the surface of your red blood cells. And so if you are Rh positive, this means you have the rhesus antigens. So therefore, you do not make any of the anti-Rh antibodies, and you can accept both positive and negative Rh blood. However, if you are Rh negative, you don't have the antigens. So you're going to make those anti-Rh antibodies, meaning the only way that you can accept blood is if it's a blood type that is also Rh negative. So you can't accept any Rh positive blood types. Now, if we combine the AB antigens and the rhesus antigens and we combine them, this will ultimately create 8 different distinct blood types. You'd have A positive and A negative, B positive and B negative, and so on and so forth. And so that's going to actually go ahead and wrap up our discussion for part 2. Again, we went into how blood cells are formed, the process of blood clotting, and some details about blood types and the consequences of those for receiving blood transfusions. And that's going to conclude our Module 2 lecture presentation, and I hope you found this helpful.